So thank you all for joining us today for Kunal's master's thesis defense. But just gonna give a nice introduction to Kunal and then pass it on. So Kunal goes by they, them, is a soil nerd who's deeply curious about exploring and deepening BIPOC relationships to land, sky, and water. They love cooking, coding, the ocean, and seeing QT2S BIPOC experience uninhibited joy. They were raised by communities of people and plants in traditions of Genesium, gardening, spices, queerness, transness, which inform all the work they do. Kunal is also a critical ecologist and terrestrial biogeochemist currently working at the intersections of pollution, community-based research, public health, and environmental justice at the University of Arizona on occupied Tohono O'odham and Pascua Yaqui lands, so-called Tucson, Arizona, in the Environmental Science and Health Risk Laboratory, and Dr. Sud Puri's critical ecology lab based on the Chinoa-Onoli land, so-called Berkeley, California. On a personal note, it's been a great pleasure working with Kunal. So Kunal joined my lab and research team in August 2019. They arrived and truly hit the ground running. In this time, they have demonstrated outstanding work ethic, as well as their ambition and creativity. It's refreshing to have a student come into graduate school already instinctively integrating social, physical, and the natural sciences to develop sustainable answers to the environmental challenges we face today. Kunal is, as stated in their bio, is rooted in critical theory and social justice, and is successfully blending qualitative and quantitative data, which is providing a unique voice to the field of environmental health. They are also intrinsically motivated to ensure that their skills in research is applied and informed by marginalized communities. And there's so much more that could be said here. I want to make sure that we give Kunal enough time, but just another, before they started their master's at the University of Arizona, they served as a student empowerment coordinator at the University of Vermont. Within 5 months of that position, they were integral in the student initiatives and university-wide professional development training. They are currently serving on several committees here in Arizona and advocating for structural changes at the university, college, and departmental level and within our community. And as stated in their email signature, they state, my environmental work is meaningless without centering Black liberation and Indigenous sovereignty. With that said, Kunal is committed to inclusive research and asking difficult but critical questions. And so with that, I would like to pass the mic to Kunal for their master's thesis defense today.
Thank you, Monica. I'm nervous and excited and happy to see everybody here. Can you see my screen for my slides?
Yes, that's correct. You're good.
Okay. And I'm not going to really monitor the chat throughout the presentation. I'll look at the end once I'm done. Just a heads up to everyone tuning in. And if you could keep yourself on mute, that'd be great until the end. Okay, so I'm going to start. And my thesis defense is titled Data Science for Environmental Justice, Community-Based Rainwater Harvesting and Environmental Monitoring in Arizona. I'm going to start by going through how I ground this work in systems of oppression and environmental change. And I'll talk about Project Harvest, the study that I'm a part of, and we'll get into the research questions informed by all of the communities and researchers involved, and then we'll get into methods, results, and the major takeaways. But I want to first acknowledge the lands, airs, and waters that make this research possible and relevant, in addition to acknowledging the ongoing colonization, genocide, and dispossession that make this research possible, particularly because this work was conducted on occupied Tohono O'odham and Pascua Yaqui indigenous lands at the land grab University of Arizona, in so-called Tucson, Arizona. And the samples in the study were collected from around the state on unceded traditional homelands of Tohono O'odham, Pascua Yaqui, Chiricahua Apache, Western Apache, Yavapai Apache, the San Carlos Apache, Pueblo, Havasupai, Hualapai, Hopi, Zuni, and Dene, and more tribes and groups unnamed and unknown to me. The United States also would not exist, and this university would not exist without the enslavement and forced labor of African people by Europeans and the continued subjugation of Black people, Indigenous people, and Black and Indigenous people by the state. I honor these unnecessary pains and harms and know that liberation and our freedom lie outside of academic institutions. And I struggle with the contradiction of being within these institutions daily. And I have to remind myself that most of my efforts must lie outside of these institutions and inside my communities. And to that end, I want to name some of the systems of oppression that influence environmental change, such as white supremacy, colonization, and capitalism. I'm not here to prove that these systems exist or prove that they do influence the environment. Rather, I'll use Project Harvest and the information that we all gathered together to explain how they influence the environment. This figure shows many of the intersections between the systems of oppression, and I want to draw your attention to the relationship between colonization, capitalism, and various supremacies down in this corner on ecocide and extraction of natural resources. And that people and scientists are already studying these relationships. We know that humans have a disproportionate impact on the environment, and there's a term that's been created and is used commonly called the Anthropocene to describe this. But others have furthered this line of thinking to really deepen and clarify what Anthropocene means, because not all of humanity has the same impact, and those more guided by these systems and by these supremacies have that disproportionate impact on the environment. But then the burden of environmentalism and activism and protest and freedom is often forced onto the most marginalized individuals and communities who are not the ones from these extractive industries, working from these systems of oppression, like many governments and corporations. And in that vein, the next few slides, I'm going to talk about how mining fits into this framework and is related to systems of oppression. And I'll be going through photos from all 4 of the communities in Project Harvest to show what the communities look like and elaborate more on mining. There are over 380 active mines in Arizona, and this state is the second in the country for most non-fuel mineral resources extracted. Mining has been linked to negative human health impacts, environmental injustices, militarization, pollution, anti-Blackness, land theft, and more. And we know many of the impacts of mining and some of the drivers. But when we stop and ask ourselves, why does this mining exist? Why does industrial mining exist? It's because of some of the systems of oppression that I named earlier. Colonization and Western ways of relating to the earth caused white settlers, to steal land and industrially mine the earth for capitalist resources to fuel the US empire and further land gain. And to address some of these, Project Harvest was created. This is where the study comes in, which is a co-created community-based project looking at addressing specific environmental injustices and environmental health injustices in the 4 communities I just showed, hoping to intervene on some of the negative impacts caused by various toxic release sites, industries, and so on. The study, again, is in 4 communities in Arizona and is built from community feedback, needs assessment, working with the City of Tucson Water, the Sonoran Environmental Research Institute, community members, researcher background, and more. And we involve community members in every part of the scientific process. And together, we are monitoring the quality of harvested rainwater, residential soils, and garden plants for 33 inorganic, organic, and microbial contaminants. To dive into the communities again, just to really drive it home, Dewey-Humboldt is a rural community in northern Arizona, which is the site of the Iron King Mine and Humboldt Smelter Superfund site, and is impacted by different legacy mining. Globe Miami is a rural community that is the site of the Freeport McMoRan copper and gold mine, which is an active mine. Tucson, Arizona is the one urban community in the study, and it is a city in southern Arizona that is impacted by various toxic release sites and has 9 government cleanup sites. And finally, Hayden, Winkelman is a rural community that is the site of the ASARCO Copper Smelter, which was active for most of the duration of Project Harvest. Participants and community members in all 4 of those communities are involved in every part of this research process, from defining research questions, collecting samples, analyzing the data, results, and then developing new ideas and next steps. The participants in the study are also diverse, with the majority of participants coming from low-income households, not having college degrees, and 50% identifying as people of color, and 25% speak Spanish as their primary language. And so all these people and researchers and communities inform the research questions, which are the ones we focus on today, are that: is harvested rainwater safe for garden irrigation? What is the quality of rooftop harvested rainwater in Arizona? Does rainwater harvesting infrastructure influence that quality? And do sites of extractive industry influence that quality? And here you see a photo of a Hayden science teacher during a training collecting harvested rainwater samples from a cistern, which leads me to the next slide of the methods. How did we answer all these questions? Participants collected harvested rainwater samples and field blanks 4 times a year at the first and last part of the winter, first and last part of the monsoon season, rainy seasons. And then the samples were analyzed by the Arizona Lab for Emerging Contaminants for various metals in units of micrograms per liter, which is about 1 drop of water in an average size swimming pool. So they were analyzed in the lab and then analyzed on the computer. Results were looked into further. And then a big part of Project Harvest is the data sharing. We hosted yearly data sharing events. In COVID, we had Zoom data sharing events. We had interviews and focus groups, art installations, booklets, presentations, community presentations, and more. But we're going to focus in on the inorganic data, results from the harvested rainwater specifically. So keep in mind that all the information you'll see in the next slides are about the rainwater, but future work will focus on soils and plants also. And we're honing in specifically on arsenic and lead in this thesis because of their primary community concern and primary health concern. These 2 slides give some background on those contaminants, detailing that they're both naturally occurring. So they're found in soils and groundwater, and in Arizona, a little bit higher concentrations than other parts of the country. They're both related to various industrial activities like mining. Lead has been used in paints, batteries, and so on, and both have a variety of negative health impacts, including cancer. And according to the World Health Organization, there is no safe level of lead. So the first question we want to answer is the rainwater safe for garden irrigation? One of the main ways to assess this is to use regulatory standards. So we can look at various federal and state standards to assess quality. And we use these 5 in Project Harvest for the most part, ranging from surface water body contact standards, drinking water standards. And because most of the participants in the study use their rainwater for gardens, we're going to focus on the United States Department of Agriculture agricultural irrigation standard, highlighted here. And if there's an exceedance of these standards, then we talk one-on-one with participants about what that means and potential next steps. So in terms of the agricultural irrigation standard, it is a permissible limit of pollution set based on accumulation of contaminants in soil from using contaminated water that could have a health impact on soil biota, other wildlife, and eventually plant life. It's not directly a human health risk standard. And in our study, 1 sample out of 577 rainwater samples collected over 3 years exceeded the level for arsenic, and none for lead. So this indicates that based on regulatory standards, the rainwater is safe for garden irrigation in terms of arsenic and lead, but we can't be complacent with our analysis and remediation because just because there isn't an exceedance doesn't mean there's no risk associated with the rainwater. And so then the next question to answer is, what's the quality of this rainwater in general? We want to know what's going on in these cisterns and what is potentially influencing the concentrations of metals here. So one way to assess this is to compare the Project Harvest data to background values, or sky water values, as we've called it. So we partnered with the National Atmospheric Deposition Program, which has been monitoring rainwater since 1978 to assess the quality of rainwater in more natural sites in Arizona. So these 5 locations in purple are NADP sites that are in more natural areas, further away from cities, further away from industrial activity. And you can see the Project Harvest communities tagged in orange here. And so the purple locations have samplers that look like this, where they're collecting rainwater without any kind of harvesting infrastructure. So there's no roof or cistern or gutters associated with them. They're collecting rainwater straight out of the sky. And they're also, the samplers that we used only have wet deposition samples. There's only rain coming when it's raining. When there's no precipitation event, the sampler is closed. So there's no extra input of dry dust. And so we average these skywater sites together to consider like Arizona background levels. To analyze all this data with the Project Harvest data and integrate various data sets, we used models, which are equations that we can look at to assess the impact of certain variables of interest. And we used specifically mixed models for the most part to account for repeated sampling from the same homes and communities over the course of the study. And this shows in a simplified example of what a model looks like, where we can look at lead concentrations in the rainwater as a function of community and season, and test, does lead vary by community and season significantly? And for the purposes of this thesis, for the most part, we used post hoc tests that were pairwise least square means tests with the Tukey p-value adjustment. So looking into what those significant differences were, for arsenic, I'm going to show, and for arsenic and lead, I'm going to be showing effect plots for the next few slides. And effect plots like the one here shows the estimated mean value from the modeling process with a 95% confidence interval in these colored dots in front with the real data in the background. And all the data has been natural log transformed for the purposes of modeling, so pay a little bit more attention to the trends and not the exact values you see. So the model will take all of this real data in the background and calculate this mean and error or confidence interval, and then compare the means to each other and see if they're significantly different. For arsenic, we see that the first part of each season, or the sampling period, is significantly greater than the last part. We also see that the monsoon season is significantly greater than the winter season. For lead, we see this similar seasonal trend, with monsoon having higher lead concentrations in the rainwater than winter. And this could be due to increased storm and dust activity during the summer rains than the winter rains, buildup of dust on roofs during the dry season, and other meteorological reasons. There's also some research that shows that industrial activity is a little bit more increased in the spring compared to other parts of the year, and that could contribute to why we see slightly higher values in the monsoon. Looking at community differences, this shows effect plots for arsenic by community, again with the mean estimates and the real data in the background, community on the x-axis. We see that every single Project Harvest community has significantly greater than skywater values. And we see that Hayden Winkelman specifically has greater values than every other community. And so it's interesting to note that Tucson, the urban community, behaves, we're observing similar arsenic dynamics to Globe, which is an active mining community, and Dewey-Humboldt, which is a legacy mining community. And that Hayden Winkelman, a community that has an active copper smelter, has the highest concentrations. Looking at lead now, we see that Hayden Winkelman and Tucson have nearly significantly greater values than skywater and are significantly greater than Dewey-Humboldt. Now we're seeing that the urban community and community of Hayden Winkelman are behaving, or we're observing similar lead dynamics here. So in general, we see that there is anthropogenic influence, meaning higher than background or natural levels of arsenic in all the communities, and of lead, and potentially in Hayden Winkelman and Tucson. And above all, the most significant variable in both these models was season, where monsoon was greater than winter. So we're starting to put together a picture of what's going on with the rainwater. We see that in general, based on regulatory standards, it's safe for irrigation. There are seasonal differences, there are community differences, and now we want to know, are there differences based on rainwater harvesting infrastructure? So does what your roof is made out of or what your cistern is made out of contribute to contamination of the rainwater? To answer this question, we combined the Project Harvest dataset with home description survey responses. And this was a big survey that the promotoras or community health workers administered to participants, asking all sorts of questions about their house and different practices. And we focused on these 9 for arsenic and lead. What is your roof made out of? When was your house built? Has your home ever tested positive for lead paint? Is the paint peeling on the outside? Is your home within 2 blocks of a major roadway? What is your cistern made out of? How old is your cistern? Does your cistern have a first flush? And does your cistern have a screen? So when we looked at these variables, controlling for the seasonal and community variables that I just showed you, we found that only home age and cistern age significantly influenced arsenic and lead concentrations. Variables like what your roof was made out of or what if your cistern had a screen did not influence arsenic and lead. So looking at that trend, we see that older homes have higher concentrations of arsenic and lead. This again shows an effect plot with home age by decade on the x-axis for arsenic, and then lead on the right. And we see decreasing trends here. Newer homes have lower concentrations of both contaminants. And then for lead, we see that older cisterns have significantly greater concentrations of lead than younger cisterns. And this could be due to older homes using different materials that could be more contaminated with those metals or metalloids. Older homes might also be built closer to industry or mines, and there could also be a relationship between maintenance and how often older homes and older cisterns are cleaned. But in general, overwhelmingly based on all the home description survey questions we looked at, individual choices about infrastructure don't contribute to contamination. So we're seeing that individuals in environmental justice communities here are not contributing to the contamination, they're experiencing it. And so to deepen this analysis, if we're seeing this community differences, there's seasonal differences, there aren't really infrastructure differences or individual choices impacting contamination. We want to know, do sites of extractive industry influence the quality of rainwater? How does mining and militarization influence rainwater quality? To do this, we looked at each community individually and assessed place-based, community-informed, unique variables for each area. And so starting with Dewey-Humboldt, this shows a bird's eye view of the area with the tailings from the Superfund, the Iron King Mine and Humboldt Smelter Superfund site tagged here is west and east. And then we categorized all the sites in the study by their relationship to those tailings. So northeast, northwest, northeast, south. And when looking at those variables, these bottom 3 are the ones we'll focus on because we've already looked at seasonal and time of year trends. And we found that for arsenic and lead, for arsenic, none of these unique community variables were significant, but for lead, location was. So looking at that trend, this plot shows geometric mean concentrations, minimum, median, and maximum values of arsenic in the rainwater. And we see there are no significant differences by location here. But for lead, there was significantly greater lead in the northeastern community than the northwestern community. And there were no significant differences by distance from these tailings that you see in the background. Moving on to Globe Miami, we split the sites and homes up by location in Miami Claypool, which also includes Central Heights, Midland City, and a high school, the city of Globe here, and then Canyons area, which includes Ice House Canyon and Six Shooter Canyon. And then you can see the boundary of the Freeport McMoRan copper and gold mine here. And for Globe, we looked at location and then distance from that mine boundary. And found that location was not significant for arsenic and lead, but distance was. Looking at that trend, we see that in this effect plot, which shows a trend line and error with real data in the background, further way from the mine you get, so further along this x-axis, the lower, significantly lower your arsenic concentrations were. And then looking at lead, it's a similar trend. Further away from the mine boundary, there were significantly lower lead concentrations. And now looking at Tucson, this shows a city ward map of the 6 wards color-coded and numbered, and I've added a star to indicate the location of the Davis-Monthan US Air Force Base. And we chose this Air Force Base to model contamination by because according to the US EPA toxic release inventory site data for 2018-2019, this Air Force Base was the largest contributor of lead and lead-based compounds to the environment in all of Pima County. And in general, the area that the Air Force Base is in is more industrial. There's the airport, Raytheon Missiles and Defense has locations there, and it's a more industrial part of town. So this distance from the Air Force Base also acts as a proxy to distance from general industry. So when looking at ward and the distance, we found that for arsenic, ward and distance were not significant, but for lead, distance from the Air Force Base was. So first looking at ward, this should be for arsenic and lead, not just lead. We see here geometric mean concentrations in the rainwater by ward, no significant differences for arsenic, and for lead, no significant differences. Even though the values in ward 4 are lower, it was not significantly different from any of the other wards. And now looking at lead, we see on this effect plot, showing lead concentration on the y-axis and distance from the Air Force Base and general industrial area on the x-axis. Further away from the Air Force Base, there were significantly lower lead concentrations. Finally, looking at Hayden Winkelman, we see the ASARCO smelter tagged in the middle here, Hayden to the left and Winkelman to the south, and ASARCO tailings way to the west. And when looking at these variables, location, distance from the smelter, and distance from the tailings, we see for arsenic, location and distance from the smelter were significant, and for lead, just distance from the smelter was significant. And looking at this trend, again, effect plots, showing that further away from the copper smelter, there were significantly lower arsenic concentrations and significantly lower lead concentrations. And then there was also a location difference for arsenic, where Hayden had significantly greater concentrations than Winkelman. And this could be due to wind direction, topography. A high school teacher in town noted that there is a hill between the smelter and Winkelman, which could be influencing the values we see here, blocking some of the potential contamination. And then also during Project Harvest, there was a lot of political and social organizing going on, where workers and the union at the ASARCO smelter went on strike and effectively shut down smelting operations starting on October 19th, 2019. And Project Harvest was still running during this time, and so we were able to have a natural experiment to look at the immediate impact of shutting down smelting operations on the local environment. And we see that arsenic decreased once the smelter shut down. This shows winter data, arsenic geometric means, minimum, median, and maximum values for Hayden on the left and Winkelman on the right, while the smelter was operating in purple and while it was shut down in blue. And you can see this decrease here. So in general, we see that season is the most significant influence on arsenic and lead concentrations, but that proximity to industry such as mines and smelters is important as well. And that we know from earlier that industry is related to systems such as colonization, land theft, capitalism, and impacts the most marginalized communities who are not contributing to the contamination of their own environment, but are burdened with it. And then we also see in Hayden Winkelman that provides a story that provides us a glimpse at another perspective that positions systems of liberation in environmental change, not just systems of oppression. So we see that the strike and union organizing, shutting down the smelting operations, could be seen as a function of liberatory practices and movement building. And we see that it's associated with decreased arsenic contamination. So conclusions from the whole study are that in terms of arsenic and lead, rainwater is safe for garden irrigation based on regulatory standards. But I want to warn against complacency because even the most well-kept and well-maintained infrastructure systems could be impacted by industrial activity, and the human health risk is not zero associated with that rainwater. And standards are informed by feasibility of cleanup, socioeconomic development, and exposure assessments. And they set essentially permissible levels of pollution. And the trends of standards over time are that they're decreased. And so in order to understand and prevent possible future contamination, it's important for us to understand the dynamics now, especially with an increased reliance on harvested rainwater due to climate change and water scarcity, and an projected increased industrial activity. It's important to know how to prevent future contamination while keeping marginalized communities at the forefront of our work. These major findings also direct our attention to the role that systems of power play in environmental pollution and who bears the burden of extractive and capitalist forces. Because we see that individuals aren't contributing to contamination of their rainwater, and that decisions they make don't have too much of an influence, but decisions that corporations and governments make do have an impact on contamination. So I want to end with this call to action to really understand the interplay between systems of oppression, systems of liberation, and the environment. I want us to clarify what we mean when we say anthropogenic, and here we really mean industrial, and identify some of the root causes of contamination as racial capitalism and colonization. And that we don't necessarily need more research, we need more action to support liberation. And that any environmental work that lacks a critical power and privilege analysis is incomplete because it ignores the realities and context of these systems here. And specificity allows researchers and everybody to pinpoint the root causes of our environmental changes and best address them. And in this study, we use environmental justice and public participation in scientific research, community-based research frameworks to best center and support the people most marginalized by these systems. So I want to say thank you to everybody who attended, all the community members, of course, the promotoras, all the students, the researchers, my committee, my PI, Dr. Monica Ramirez Andriota, Dr. Rob Root, Dr. Sandlin Buxner, and also want to give a shout out to the Critical Ecology Lab and Dr. Sue Pierre, where a lot of this critical theory was first developed. And now I'll have some time for questions.
All right, round of applause. All right, feel free, so feel free to unmute yourself and ask questions, or questions can be placed in the chat. All right, question in the chat from Rizka. Do you think distance from Tucson landfill might have also influenced contaminant concentrations to a lesser extent?
Yeah, that's a great question. We didn't look at the distance from the landfill, but that's something to definitely look into in the future. I'm gonna write that down, actually.
Thanks.
Any questions from the audience at this time? Getting some great shout outs in the chat. Okay, in Tucson, at least last year was very dry, and we had a poor monsoon. Do you think this affected the arsenic and lead concentration?
Yeah, so we, Project Harvest was collecting samples from 2017 to 2020, but actually because of COVID, we stopped collecting in spring of 2020. So we weren't collecting samples during last year's monsoon when it rained like once. And then even if we were collecting, we probably wouldn't have received that many samples. So I'm not sure how that would have affected this data specifically, because we didn't look at that. But if I were to guess, I would say that the buildup of dust over the very long dry season would have meant that the rainwater in the initial flush would have been a little bit would have been more contaminated, particularly for arsenic, because we did see the first part of the season was significantly greater than the last part for that contaminant specifically.
Another question, thanks Kunal, was great job Kunal. What kind of sources of lead would you expect from the base?
Yeah, so when looking at the toxic release inventory data from the Environmental Protection Agency, the Air Force Base in their reports that they put out doesn't have to say exactly where the lead or lead compounds are coming from or where they're released to. And so those reports were a little bit vague and didn't have like the specific media. Like some of the other reports, for example, the Department of Justice has a prison south of Tucson that was also a large contributor of lead and lead compounds. And they said specifically that there was lead from the firing range and going into the air and the soil. And so I would expect something similar from the Air Force Base, but it was not, they didn't report that. So that's just like a more of an educated guess there.
All right, we have a question. Were your samples filtered prior to analysis, and then what pore size? And does that have any impact on your results interpretation if folks are irrigating with unfiltered water from the carboys or the cisterns, I'm guessing?
So our sample, all the data you saw was dissolved metalloid. So samples were filtered to 0.45 or through a 0.45 micron filter. And I think that in terms of the rainwater that wouldn't be filtered, we actually also analyzed for total metals, and that was filtered after a digestion process, and so is more similar to like an unfiltered rainwater sample. And the total metals data was not significantly different from the dissolved metals, and so I would say that the data that I showed would apply to unfiltered data set as well.
We have a question. Thanks, Kunal. What other laboratory steps would you recommend that could be offered up as additional call to action?
I love that question. Thank you, Rachel. I think that really the first step is just like listening to those impacted by the different kinds of pollution or industry or any kind of like negative environmental impact. And they're the ones that live their life and experience that every single day. And so they know it best. They're experts of their own environment and sense of place and relationship. And the first step is really kind of setting aside, I think, oftentimes in academia, people have this idea that I know what's best, coming in with the solutions. And I think the first step is setting that aside and then really just supporting all the organizing and community that's already exists in these places, because there's so much resilience that's required and to stay living in these locations, and so much joy and celebration to really support. And I think that bringing in new ideas can be great, and oftentimes the people living there already know what to do.
Thank you. And I see that Flora has their hand raised.
Hi, yeah, I noticed, I'm curious because you said one of the leading factor for the variation in lead and arsenic was seasonal. Can you talk a little bit more about that? I'm just curious.
Yeah, so we see that there were higher concentrations of arsenic and lead in the monsoon, so during the summer months than the winter months. And looking at that difference, it's kind of consistent across some of the other metals that we've started to look at too. And so we're seeing that it's maybe due to more like intense storms in the summer, causing more dust activity, more soil to be kicked up potentially, and more dust to be deposited on roofs, which then be flushed into the systems. And so because the increased storm activity happens in the summer, that might be a reason why we see larger contamination. And then I did find some research that indicated that mining in Arizona and Utah is a little bit is increased in the spring which could also contribute to higher concentrations in the monsoon, more like mining activity and dust generation from that process.
All right, we have a question. Do you know what is influencing the trend in Dewey-Humboldt?
Can you elaborate which trend, or I can also go back and show those slides again?
This question was from Denise. Did you want to elaborate specifically on what trend you're asking about?
Yes. So I think you mentioned that there was an east-west trend that you were seeing between the arsenic and the lead.
Yeah, for lead concentrations, there were higher lead concentrations in the rainwater northeast of the tailings compared to northwest of the tailings. And that could be due to wind direction. There also is like a dip in the topography, so that the way the landscape could influence that. And then some folks in town have indicated that there's a little bit different industrial activity happening in the northeast corner of town. And so that could be impacting things too, but I didn't look into that industrial activity specifically.
Thank you.
All right, and I think we got 2 more questions in the chat, and I think that'll allow us to wrap up the Q&A unless there's any others. But right now we have, what are some of the atmospheric conditions that influence deposition? Will climate change impact those conditions or influence future contamination?
Yeah, I'll focus on the climate change part of that question because with climate change exacerbating droughts, water scarcity and drought conditions, there'll be drier and drier dry seasons, and therefore more dust activity, which could lead to greater deposition and greater contamination. There's also a relationship between percent plant cover and dust generation, with climate change making ecosystems, particularly semi-arid and arid ecosystems, more vulnerable. Plant cover could decrease as well, which would potentially increase dust generation as well.
And we have the question, how do your results compare with other studies on harvested rainwater?
Yeah, great question. I can actually show a slide. I have a table that compares values between a few different locations, semi-arid and arid locations. And so this first column has Project Harvest listed, and the location is in Arizona. Potential sources of contamination are mining, dust, and we see a mean arsenic value, standard deviation in parentheses, and then the range, the minimum and maximum values. And we can compare the arsenic values here to this study in Bolivia, which was also a semi-arid environment, impacted potentially by mining and dust. And we see that our values on average are lower, but the range is greater. And then this study was conducted in Hebron, West Bank in Palestine, which is also a semi-arid or arid climate. And our lead values are on average are lower, but the range is similar, though a little bit lower than the values found in this study. And there are a lot of rainwater harvesting studies in Australia, on the coastlines, in Southeast Asia, that are in climates that are more humid, more tropical, more temperate even. And when compared to I did not compare our data to those studies specifically because of the really different climates that were in those locations. So there needs to be, I believe, a little bit more synthesis of data for semi-arid and arid regions to best make some global comparisons.
All right, well, I would like to thank Kunal for their presentation, as well as thanking all of the guests who here were and asked some great questions throughout the talk. So thank you all so very much. If you definitely check out the chat, Kunal, getting some great feedback and comments. And so thank you all. We ask that the general audience leave the room now for us to proceed with the next steps of the defense. Thank you all.